where there's four descriptive features of the first four columns: weather, temperature, humidity, and wind, and one target variable of plate, which is the last column. And all of these are uh, disc- categorical features with discrete values. So basically, the goal of from this data set is to build a decision tree that predicts whether some tennis game was played based on these four columns, which represent some climate condition for a certain date. So we would want to first have some idea on what a decision tree is. So the decision tree in this slide is one form of decision tree. As you can see, it's a general tree, not a binary tree, where the root node corresponds to the feature itself. The question corresponds to the feature of weather, and its children are all the possible feature values for that particular feature. And again, the child node of one of those feature values is again a question associated with a particular feature. So we can see that for this type of a decision tree, it's basically a series of question and answers forming some specific condition. For example, if we follow the path of this path, starting from the weather, which was rainy, and the wind was also strong. So this forms a specific condition that leads to some prediction for the target variable, whether the tennis game was played or not, which here the prediction is it was not played, which is the outcome being no. So the reason I emphasize why this is one form of decision tree is because this type of general tree was used in the earlier version of the decision trees. So the decision tree we'll go over this during this today's lecture is called iterative dichotomized tree. This is the earlier version of decision tree, which uses this general tree. However, a tree can also be binary, which is used in more modern trees. So this will not be explicitly covered during this lecture, but I would like to mention this because this is used in more modern trees, which are basis of random forest or machine learning models use this modern type of decision tree, which is called CART, which is a derivation of classification and regression tree. So this CART decision tree is not based on this general tree structure, but is based on a binary tree. It will look like this. So we can see that in the general tree, the branches correspond to a particular feature value of that feature. So for a binary tree, anyone have any idea on what the branch in a binary tree would correspond to? Mm, so when we try to split in terms of binary, we can think of it as a true or false condition, which is in other words, yes or no. So based on some condition, we are branching out to the right based if that condition is true. And if that condition is false, we're branching out to the left subtree. So the counterpart, so in the general tree, we are just asking, what is the weather? Branching out to the three possible subtrees. But the counterpart in this binary tree context, this could correspond to the condition of weather being rain or sunny. So if the weather of that date is rainy or sunny, we branch to the right subtree because it's true. Otherwise, we branch out to the left subtree. So in this case, then we could think about in terms of the what would be more efficient in terms of the when we try to determine this condition, because in the general tree, it's very straightforward how many branches, what condition we should use. It's already predetermined. We have 3 branches because we have 3 feature values for this specific feature of weather. But when it comes to the binary tree context, we have this condition of whether this condition itself would have 2 to the power of 3 minus 1 possible combinations because we have 3 distinct features. So we have a power set. The number of power set for these 3 features would be 2 to the 3, and we disregard the empty set. So we have 7 possible combinations, which could be one possible case. Could you go back to the phrase slide? Yes, Rishka, I will, after the course, after the lecture, we could do it. Yep. Okay, so, yep, so there are 7 possible combinations, such as whether is in, set, rain, or sunny, and so on. There can be 3 to the combination of 2, and so on. And this number of combinations are considered manageable. So that is one of the reasons why CART is computationally, despite it's computationally more expensive than this general tree in branching out, in determining the condition, it is still mainstream in the modern decision tree choices. So, but now we would want to get some idea on why this binary tree, or what kind of advantage this binary tree has. So an example from this slide is from the weather. There are 5 instances of rain, 5 instances of sunny. I believe it's actually 1, 2, 3, 4. Yes, 5. And 4 instances of cast. So in this case, these the data at this point considers all of these 14 instances, whereas as we diverge, we're narrowing down to a subset of the original data set. In this case, the subsets are quite evenly distributed, but there could be also a case where the rain happens to correspond to only a smaller number, but only having 2 instances. That's a possible case, a likely case. And in that case, if we start branching out, starting from that subtree, then we would be generating rules based on a very small number of data instances. So we're fragmenting the data into very smaller pieces and then making extracting rules out of those small number of data, which whereas in the binary tree case, in this case, if we assume that the rain was number 2 and sunny correspond to a subset of size 5, then in the rise up tree, we will be generating branches and conditions out of a more larger number than 2 because we are dividing into 2 subgroups instead of dividing into subgroups that correspond to each feature. So in that sense, the binary tree could lead to more robust decision trees in terms of less learning from the noise, because in the general tree, if we learn if this rain data instance could correspond to some noise, so then our subsequent rules will be determined based on the noise, which is will be not generalizable to the test data, so it's prone to overfitting. So that's why in the modern decision trees, we favor the binary tree. So that's the point for this. So but in today's lecture, since this is the earlier version of the decision tree, we will progress with this form of a decision tree. So naturally, the next question would be how, given this data, when we start constructing the decision tree, the first question would be which input feature should be the basis of the root node. So that would basically gives us a need to have some kind of criteria in comparing the quality as a root node across those the input features. So in other words, how would we measure the importance of each feature? Which we are using the information theory concept of entropy, which is equivalent, it could be understood as the impurity or unorderedness of a set. And this ID3, this earlier version of decision tree, utilizes this entropy in comparing the different features in determining the next node to select the next node for branching. But other decision trees, such as which I said as CART, uses other kinds of information theory concepts such as a Gini ratio. But all of these concepts are fundamentally checking how well dividing by this feature leads to more pure subsets in terms of the target variable of the plate. And this concept I will demonstrate in the future slides. So at this point, since now we would want to determine which feature should correspond to the root node, we would want to select the feature that reduces the most entropy, which is, in other words, that leads to the highest information gain. And it's okay if it's confused so far. I will demonstrate this in the next slide. So just as a recap, we are using this particular data set, the played. Okay, the played is the target variable, and others are input feature variables. So we can think this played variable as being a set of, there are 5 nodes in this played variable. Five nodes, and 9 yeses. So when we think about the entropy of this played set, if we were to select one of this element at random, then we will get a no as a 5 over 14 probability, and we will get a yes of 9 over 14 probability. So this is quite uncertain, right? Because we might get a yes with a higher likelihood, but still it's quite uncertain whether we will get no or yes. So this set is quite impure, unordered. So this would have a high entropy, and our goal is, when we at each decision tree, which feature, if we know, say, the feature of humidity, if we knew these values, then would this help us in getting a more pure set of the played data set? Meaning, will knowing this values of this specific feature of humidity, would that help us in prediction of the played outcome? So that's the high level idea. And if anything is unclear, please let me know. I would love to clarify. So in the previous example, I've shown the entropy of the target variable of played is basically based on this probabilities of getting a yes, which is 9 over 14, and getting a no of 5 over 14. So we could do a quick recap on these concepts, which may have been covered in the first half of the course. So this is the formula for the entropy. And we're getting the weighted average because for this specific set of played, we have two categories of played yes and played no. So we want to compute the average uncertainty of this set itself. That's why we are doing the weighted average across across all of the possible categories in this set. And and this log base 2 of probability for each class, sorry about that, corresponds to the self information, which is the surprise of this, if this event happened. If the event of, in the extreme case, let's assume that if an event A, assuming that the event A of played being yes equals to 100%, which is 1, then that, if that happens, that event happens, is not going to be a surprise at all. We're very certain that that event will happen. So log base 2 of that would lead to 0. So 1 times 0 would be 0. So the entropy in that case, that set of all yeses, played equals yeses, would end up of entropy of 0 because it's a very pure set. And on the other extreme, if there's a probability that is very small, or let's assume that an event is 0% going to happen. So log base 2 of 0 itself is undefined, but since it's 0%, that is also extreme case where so this is so anyone have any remember why we take the log base of 2? Right. So this log of 2 is basically trying to quantify the amount of information, which is because basically it's trying to quantify it as a bit information. That's why it's a log of 2, the binary bit. And so now we have computed the entropy of the plate set itself directly using this formula, which is the initial entropy of 0.94, which is very high because the highest possible entropy is 1. And our goal is to select a feature, either weather or the other 3 features, that can most reduce this entropy, which is, in other words, that leads to the highest information gain, where formally this term is the conditional entropy, meaning starting from the target variable entropy, if we knew the values of a particular feature of weather, we want to know the average remaining entropy or uncertainty about the target value y, given the values of the feature of x. And now we're assuming that we know all the values of this feature. So we again compute the specific conditional entropy of the target given a feature being a particular feature value, and then getting its weighted average so that we can end up with the average remaining uncertainty of played. This D corresponds to played, the whole data set. When we knew all of the values of weather, so we account for each case, the remaining entropy when the weather is equal to rainy, overcast, sunny, negate their weighted average to assess the quality of this feature of knowing the values of feature weather, how much this can decrease the entropy from the initial entropy. Yes, so since we start from the initial entropy, we subtract the conditional entropy of knowing a particular feature, then that will return the information gain or mutual information of those two, which is the assessment of the quality of picking that feature as the next node in form of the decision tree, which if we plug in all the values, the one caveat is that since now the entropy that we're computing is in relation to the target variable, because our goal is to better predict whether it was played or not. So all of the entropies we compute are in terms of the target variable, such as when it was rainy, out of 14 instances in the original data set, there was 5 instances of the weather being rainy. And among those instances, for the played target variable, there were 3 yeses and 2 nos. So this seems to lead to a high entropy, right? Because it's 60% versus 40%. So if we randomly picked one of these from this 3 yes, 2 no set, then 60% chance to get a yes, 20% chance to get a no, 40% chance to get a no. So we were quite uncertain. Similar story for the sunny subset. But for the overcast, if we know the value of overcast, now we get a perfect division of yes and no, right? Meaning, since this set where weather is equal to overcast, if we randomly pick one element from this set, it's going to be 100% yes, which we are certain. So this would lead to a 0 entropy. So that's the idea. But at this weather feature level, we get their average weighted weights. We get their average by each weight, which leads to 0.693 of entropy. So before it was 0.94. After we know the values of the weather feature, it dropped to 0.693, which is quite a substantial drop, we can say, as the information gain. So as we have just seen in the previous slide, we computed the information gain with the feature of weather, which is 0.247. And we can compute in a similar fashion for the other 3 remaining features, each of their information gain, and compare them to each other. And the weather led to the highest information gain. So we select the weather feature as our root node. So if there's any questions, please let me know. Okay. So now, since we set the root node as the weather, it's under this scheme of decision tree, its children will be all the possible values of it: rain, overcast, sunny. And now, since this form of decision tree is a series of question and answers, we would want to pick the next feature that will come under each subtree. Actually, for overcast, yes. So we will first focus on the sunny feature in determining the next feature that will be the child node of this sunny. And another point I would like to emphasize is, given our 14 instance original data set, at this point of root node, we are considering this whole data set. But as we branch out, now let's assume that this blue subtable corresponds to weather being equal to sunny. So as we branch out, we are more and recursively and iteratively considering a smaller subset from the original data set. So basically, this decision tree is dividing the original data set more and more so that in the target variable, we want its distribution of the yes and no to be more pure so that in the end, at the leaf node, hopefully we get a very pure set in terms of the target variable of, say, all yeses or all nos. So that is basically the idea of this decision tree. Yes, so as I've just mentioned, when we try to determine which feature should come as a child node of this sunny node, then now we're considering the subset of from the original data set where the weather is all equal to sunny. So there's 5 instances as we can see. So now we want to figure out should the child node be temperature or humidity or wind, and which feature leads to the which feature makes the distribution of the plate more pure. So that is basically the question, which is basically what we have done in the previous process when we were determining the root node. We're doing the exact same process, which you see in the next slide. So now, since our starting data set, where we compute the initial entropy, is this size data set with 5 instances, we compute the entropy. So as I've mentioned, the entropy will always be computed based on the played variable, the target variable distribution, which we have 3 no's and 2 yeses. Again, is 60%, 40%. So this is also will be uncertain when we just draw one sample and want to know whether it's yes or no. Then it's quite an impure subset, as you can see, because 60%, 40%, which this will become the initial entropy, which is again a very high entropy because the max is 1. And as I mentioned, we want to figure out which remaining feature, leads to the highest drop in terms of the entropy. In other words, highest information gain. So using the exact same formula, where the entropy formula was used to compute the initial entropy of this subset of weather equals sunny, then we would want to compute for each conditional entropy the average remaining entropy of the target variable, given that we know the values of this particular feature, in this case, the humidity. So we know that if we know the humidity, because in the previous data set, we've seen that there are 3 no's and 2 yeses, just to avoid confusion. Here we know that if we did not know any of these features, just knowing this weather variable, there are 3 no's and 2 yeses. But let's say now we get to know the humidity feature values. If we know these two, if the humidity was all high, So for the humidity equal high feature value, if we condition the data set on this humidity equals high, then it's all no, right? The plate is equal to all no. And also, if we knew that the humidity was normal, then it's all yes. So this means that if we have the condition weather equals to sunny and humidity equals to high, this would lead to the plate of no with certainty because it's all no, at least based on this small data set. And also, yeah, also this same case the for when we do it as normal. When the weather is sunny and humidity is normal, plate will be all yes. So this means that knowing the humidity feature values helps us in arriving to a more pure set of the plate subset distribution. Or in other words, it helps us better predict the plate outcome, which and in this table we can see that if we have did not know these, then it would be just 2 and 3. But by dividing into high and normal, we see that it's perfectly segregated, right? So in other words, since the conditional entropy of sunny, in other words, the plate valued variable distribution given the values of humidity leads to perfect segregation, naturally the resulting sets are perfectly pure, giving us the remaining average entropy of 0, which translates into the information gain of highest as possible from the initial entropy. And if we calculate the same for each of the other two variables, we get different values, which you can see that knowing windy doesn't really help, right? And temperature helps more, but it cannot beat the humidity. So that naturally leads us to selecting humidity as the child node of sunny. If anything is unclear, please let me know. Yeah. So as you can see, the child node of sunny is picked as humidity level, as in the previous slide. And again, the children of this feature node of humidity would be its all possible feature values, which was high or no. And we know that the leaf node here, this is no, is correspond to plate or yes, which the set that the data in the training data set that correspond to this yes was I was 3 no's and 2 yeses. So if we use this apply this decision tree to our training data set, it would yield 3 no's and 2 yeses for this normal feature value. So with this similar following this similar process, the other subtrees can be constructed. So one point is that depending on the data set, in this particular example, the leaf nodes are pure, meaning we end up with all 3 nodes set. for that correspond to this prediction. But depending on the data set, it's also possible that we get an impure leaf node, such as this is just hypothesizing. We could end up with a yes, yes, no leaf node set. In this case, we typically predict with the majority. So my point here is that it is not given that we always end up with a pure leaf node. It is possible depending on the data set. And if we're trying to further split, but we are not left with any more features left, then the leaf node would be impure. Then we typically pick the majority voting and take that as the prediction. Okay. So given that we have constructed this decision tree, now we would want to make a new prediction for tomorrow's let's say a forecast. Let's say tomorrow's weather forecast is sunny, strong wind, and high humidity. Then we would utilize this decision tree of going to sunny. But in this pass, we don't need this strong wind information because directly using this information of high humidity would lead to the prediction of no. And this is quite common in terms of decision tree. Not all of the feature values are used in each path. So we can think of this as the decision tree is implicitly doing some sort of a feature selection implicitly because at least in this pass, it disregarded the strong wind feature information. And as we can see, the decision-making process is very human interpretable because in neural networks or um, other more complex machine learning models, the the understanding is decision making process is more complex, but for decision tree is basically very transparent. It's almost as a if else condition rule. So that's another feature of the decision tree. But the decision tree is generally um, by itself. It's in the high level that this it can be prone to overfitting, and that overfitting problem is as the decision tree gets deeper and deeper. This specific example is based on a small data set, so the rules are quite simpler. So rather, this could lead to underfitting in the test data, but the general disadvantage of the decision tree itself is that it's prone to overfitting as it gets deeper and deeper, such as having multiple levels until it reaches the leaf. So that's a tendency. And that actually motivates the trying ensembling using the decision tree, which we will go over in the next slide. So the ensemble method is basically based on the idea. So the core principle of this ensemble method is that uh, it's like democracy. So the collective decision of um, non-experts can be more effective than the decision of a single expert. So, formally, one way to say it is wisdom of the crowd, which is the basic idea um, behind this approach of ensembling. So, in other words, is aggregating the weak learners, the less experts or non-experts individuals, and aggregate them in order to come up with a strong learner. So in this case of our uh, decision tree, one more complex version of a decision tree would be having a very deep decision tree, whereas a weak learner in terms of the decision tree would be called the tree stump, decision tree stump, which is a shallow one. So instead of constructing one complex model and relying on the single learner, we are training multiple weak learners, which are diverse, that I will explain, and then aggregating each of their idea and then going through some democracy process so that we can tackle the tasks from different aspects so that we can combine the strengths of those individual models and mitigate their individual weakness through the the voting, which the idea is by doing that we can beat the single expert. Let me know if anything is unclear. So in this case, now we know that we are using many weak learners. But if those weak learners are if they learned basically the same thing, then they'll produce same predictions. Then voting, going through the voting of those would be trivial. So that means that the individual weak learners, there should be some diversity across those weak learners. This doesn't mean that they should learn something entirely different because we're still tackling the same problem, but the individual weaker, more simpler learners should at least learn something different from the other fellow learners so that they can have some different opinion about the problem so their collective decision is more rich compared to one single expert, which that single expert may be an expert itself, but because of being alone, it may have its own biases. So that's the basic idea of having diverse weak learners to aggregate their decision to beat the strong single learner. So that means that diversity basically translates into combination of different models. In this case, is referring to one learner could correspond to a different model. One can be SVM, which we learned. Another could be decision tree, and so on. And another example would be the same model with different size, which in context of neural network, we can think of it as we want the learners to all be neural network, but we want one of them to be shallow and others would be sequentially deeper or wider. As the model complexity increases, its learning capacity increases. So, and they all tackle the same problem. So each of them might learn something different based on their different features on the same task. So we're tackling the same problem from different perspectives and then aggregating them in this case. In this case, the same model with different sizes. Or we could use the exact same model, not as SVM or decision tree, but we could use the exact same model as decision tree, but train them on different set of data. And this we'll go over in the next slide, which course which relates to the concept of bootstrapping. So basically, before diving into the bootstrapping, bagging is a corresponds to bootstrap aggregation. So we're performing bootstrapping first, which I will explain. And then based on that, we might get some multiple predictions or train multiple models, then aggregate their decision for the ensemble learning, which we talked about. So the bootstrapping idea is that if we have an original data set, so bootstrapping is basically a sampling method, such as if we have an original data set, of n samples, or we could just use m samples. We random sample, we construct a new data set based on this original data set with the same number of instances, which is m samples again, but we sample this, let's call as bootstrap sample 1 or bootstrap dataset 1. But if we do not allow sampling the same data point again, then if we just sample without allowing any duplicate sampling for the same data point, then we will get the exact same data set. It is clear? If anyone's confused, please let me know. So formally, bootstrap is correspond to sampling with replacement. In other words, when we sample a data set from the original, when we sample a data point from the original data set, we're allowing to sample the same data point multiple times. Say data point 1 can be sampled again. Then in the bootstrap data set, we might end up with some data points being duplicate, appearing multiple times. So this means that the bootstrapped data set has the underlying data distribution of the bootstrap data set is basically the same, similar to the original data set, but some of the data points in the original data set are not included in the bootstrap data set because some are duplicate. Because if some are duplicate, some are ignored. And so we can interpret this bootstrap data set as a data set that is slightly varied from the original data set. Same task, but there's some variation. And then we generate these types of bootstrap data set for n number of those, which is n bootstrap samples. We have n number of these slightly different data sets from the original data set. So If we train a model, say a decision tree, the same model but different instances of the model, actually here, model 1, model 2, each of them on this bootstrap dataset, these models, decision trees, will learn something slightly different. The same task data distribution, because they all originated from the same original data set, but they are slightly different due to the bootstrapping, the with replacement condition. So these models, set of models, would have their own opinion about the problem, which is there's some kind of diversity in what they've learned. Which this diversity is basically aligns with the idea of the ensembling, the the diversity across the weak learners um, beating the single strong learner. So this weak set of weak learners. Now, since we covered the bootstrap case, so there they will make some prediction given some test data set. And then it would be aggregated, which typically one case is to use majority voting, which is just simple. If the model 1 said yes, model 2 said yes, model 3 said no, then we go with the yes, which is the majority, which becomes the final prediction. And the important point of this bagging is that the models are homogeneous, and the random forest, which popular machine learning algorithm, which many of you might have used or learned, is basically applying this bagging to the decision tree. There are some more tricks to this, but that you could, if interested, you could let me know. Could discuss. So the next ensemble technique is boosting, which we will not go into too much detail, but the idea of the boosting is same as the bagging in the sense that we again have a set of models which will be used to compute combined model, set of models, model 1 to n, which will be used to generate the final prediction. But for the boosting, the general idea itself is that when we train a sequence of models, the subsequent model, which is model 2 to model 1, the subsequent model will try to learn from the mistakes of the previous model. Model 2 learn the mistakes, learn from the mistake of the model 1, and model 3 learn from the mistake of model 2, and so on. So that is the general idea of boosting. And in this slide, this slide basically covers one specific category of boosting, which is gradient boosting, which we compute the residue here. So it's called gradient because we are basically in this slide is not explicitly shown, but if our loss function, so mean squared error like this, then if you get it's a gradient with respect to the model output, which is y hat, then that would be which is basically correspond to the residual. So the residual here, you can just think that they're basically the gradient of the loss function with respect to the model output, which is the residual when you compute. So in this case, the first model's mistake would be the error, the residual, the subtraction of the target from the model output. And then the second model 2 will try to correct the subsequent model's residual, the mistake, and so on. So the models are collectively, incrementally trying to decrease the bias as a whole, which the gradient boosting decision tree, gradient boosting, is applying this boosting idea to the decision trees. And there is another boosting algorithm called adaptive boosting, which you might see in the future or have seen, is shares the idea that the subsequent models learn from the previous model's mistake, but is a different idea compared to this of correcting the residual. So that I would like to mention. And for boosting, also the models are homogeneous, such as using the same model type of decision tree and so on. Yeah. So the last ensemble model technique is the stacking, which is different from the previous two ensembles. The previous two ensembles are homogeneous ensembles, meaning the underlying base learners, base models are from the same data type, same model type. But for the stacking, each model are typically heterogeneous. So for example, model 1 could be a well-trained SVM, model 2 could be a decision tree, and model 3 N could be something else. So that's the first difference, that stacking is heterogeneous, whereas the other two was homogeneous. The second difference is that the other two models operated basically try to directly utilize the prediction, meaning that for bagging, if model 1 makes a prediction of yes, model 2 makes yes, model N makes no, then we directly apply a voting on these predictions to come up with the final prediction of yes, which is the majority vote. Whereas for the boosting, we also directly use in the testing, we directly use their outputs, such as if you're given a test data, the model 1 will make its own prediction, which is y hat, the output, and the subsequent models which are trained to correct the previous model's mistake, will again generate the estimated residuals, which are all of these are predictions, which are directly added to each other to get to arrive to the final prediction. So we're directly utilizing the predictions, but for the stacking, we are generating a new data set based on model 1, model 2, model 3's prediction. So visually, let's say our original data set has a target of, let's say it's a binary classification task, so on. And the original data set have its own numerical values. This can be anything. Original data set feature values can be anything. And the base models, model 1 to model 2, will be trained on this training data set. And then for each data instance in the training data set, it will make its own prediction. Model 1 would say, think should be predicted as 1. Model 2 should think the prediction as 0, and so on. So because for the bagging, we simply applied majority voting to each of the models' prediction to get the final prediction. But for the stacking, we treat these predictions as a new data set, which is used to train the meta model, which could be, say, a logistic regression model, which tries to map the predictions of the base models to predict the true label of true. Yes, here. So it's trying to learn how to intelligently weight the base model's prediction in predicting the final prediction, not just trivially majority voting as bagging does. So there's more sophistication to its decision-making process. So the key point here again is that for stacking, it is heterogeneous. So in case we have already good, well-trained separate models in the scenario, then we could, and they are heterogeneous, meaning we have a well-trained SVM, we have a well-trained decision tree, and so on. Then we could apply stacking because, okay. So the last part of the lecture is a relatively simple concept of the nearest neighbor algorithm, which is a supervised learning algorithm. This nearest neighbor algorithm is the basis of the KNN, K nearest neighbor algorithm, which is easy to confuse as KNN to an unsupervised learning algorithm, which we'll go over in next courses, called K-means. It's very common to confuse these two. So KNN is a supervised learning algorithm. We're trying to predict something based on the labeled data. And K-means is unsupervised learning algorithm. So that you would want to make sure to remember. And the idea is very simple. You have a training data set and you have a test data set, a test data point. You compare the test data point against each of the training data set instances and then find the most similar training data instance within this training data set, similar in terms of the feature value. Then make a prediction of the test data set as same as the most similar training data instance, which we will see in the next slide. So given that this is our training data set with two features, x1 and x2, and their labels are associated labels are 0 and 1, which you can see of it as the red square and the blue diamond. Let's say that we have a test data instance of x1 8.1 and x2 3.36. So in this 2D feature space, it would be somewhere here, which is basically in this region of the red square data points there, and the closest data point, training data point, is this red square. And the true label of this test data is again 1. Sure. Yep. So, gosh. Okay. So here what's happening is basically we are computing the Euclidean distance from the test data point to each of the training data. Test minus x1, each of the training data in the 2 dimensions. So that we compute the distance of the test data against each of the training data. So naturally, this would be the basis of our prediction since we're trying to identify the most similar or the nearest neighbor. So this is what's happening during the test phase of the KNN, the distance computation. which in the KNN, since the K is a hyperparameter, if K is equal to 3, we find the 3 nearest neighbors, which have which their associated labels are ones. So we do the majority voting, which is again 1. So the test data will be predicted with a label of 1. So that means that the K should be an odd number, because if it's an even number, there could be ties. So lastly, for the KNN, as we have seen, the distance computation of the KNN correspond to the testing phase, meaning that in the training phase, we're not actively learning anything. So KNN, which does not do anything in particular other than storing the data set, is formally called a lazy learner, whereas other algorithms, machine learning algorithms such as SVM or logistic regression or others, which try to train some weight, are eager learners. So KNN does not do anything in particular during the training, but during the testing, it computes the distance and then uses that distance to identify the closest ones and do the voting to make a prediction. So this is very easy to implement. During the testing, we just compute the distances. Easy to implement. And also, as the second bullet point says, when we get new labeled instances, since what we do during the training is only storing the training data set, we simply add that new labeled instances to the existing training data set. So updating the model is trivial. Whereas for other types of models, such as neural network, there may be cases where you would want to augment the data set and then retrain it, which could be costly. So the disadvantage is that it is trivial that we just store the training data set, but if the training data set size gets very large, then that would be an issue. There will be some incremental overhead from storing it, especially when we try to. It could add complexity when we try to call it into the memory from the disk. And also, since we have to compute the distance for each training instance against the test data, that distance computation can be very expensive when the data set becomes very large, which would end up computationally expensive. So those are basically the trade-off of the KNN. So that was the end of the lecture. And so I think Rishka asked for. Yeah, so first of all, I have posted the final project and assignment 3 on Brightspace. So if anyone has any question, you could let me know using this time. And for Rishka, I can show you the